In RF systems, signals never pass through a system unchanged because every component modifies amplitude, phase, and shape in a predictable way over time. To analyze this behavior mathematically, we need a framework that connects input signals, system properties, and output signals. Convolution provides exactly this fundamental relationship. Convolution is a mathematical operation that describes how an input signal is transformed by a linear time-invariant system. Instead of treating signals and systems separately, it combines both into a single process that directly produces the output signal. This makes it one of the most important tools in signal processing and RF system analysis. The key idea behind convolution is that any input signal can be decomposed into many small, impulse-like components. Each of these components passes through the system independently, and the system responds to each one according to its impulse response. The final output is the sum of all these individual responses. This framework is essential because it allows engineers to predict system behavior without simulating every internal physical process. It replaces complex circuit dynamics with a single mathematical operation that fully describes signal transformation in time. The impulse response represents how a system reacts to a very short and idealized input signal. Although perfect impulses do not exist in practice, this concept is extremely useful because it captures the complete dynamic behavior of a system in a simple mathematical form. When a real signal enters a system, it can be viewed as a sequence of small impulses distributed over time. Each impulse triggers a scaled version of the system's impulse response. These responses overlap and accumulate, creating the final output signal. This interpretation shows that convolution is essentially a process of accumulation over time. The system remembers past inputs, and its output depends on how all previous impulses interact through the impulse response function. In the time domain, convolution can be understood as a sliding and overlapping operation between two functions. One function is flipped and shifted across the other, and at each position their overlap is computed as an integral that produces the output value at that moment. This process reflects how real systems behave with memory. The output at any time depends not only on the current input but also on past inputs weighted by the system's response. This is why convolution naturally describes filtering, distortion, and temporal spreading effects. Although this operation may seem complex mathematically, it directly represents physical signal processing behavior. Every point in the output is the result of accumulated interactions between the input signal and system characteristics over time. One of the most powerful properties of convolution is its relationship with the frequency domain. In time domain, convolution is an integral operation, but in frequency domain, it becomes simple multiplication. This duality dramatically simplifies RF system analysis. This means that instead of computing complex time domain overlap integrals, engineers can transform signals into frequency domain, multiply their spectra, and transform back to obtain the output. This is one of the core reasons Fourier analysis is so important in RF engineering. This relationship also explains why filtering is easier in frequency domain. A filter's effect becomes a simple multiplication of frequency components, making system design and analysis much more intuitive and efficient. In RF engineering, convolution describes how real signals are modified by physical systems such as filters, amplifiers, antennas, and communication channels. Every system has an impulse response that determines how it shapes incoming signals. For example, a bandpass filter selectively removes unwanted frequency components by shaping the output based on its impulse response. Similarly, wireless channels introduce delay, fading, and distortion, all of which can be modeled using convolution. Because of this, convolution is a foundational concept in RF system design. It connects time domain behavior with frequency domain analysis and provides a complete mathematical framework for understanding signal transformation in real communication systems. Convolution describes how input signals are transformed by systems through impulse-response interaction. It connects time domain behavior with system memory and output formation. This concept is essential for understanding filtering and RF signal processing systems.